Using the fundamental theorem of calculus 1 notes. So we're going to start by doing a what I suppose would be called a review problem. Here, example 1, we're looking at this function, the square root of 32 minus 2x. The function is graphed over here. We're looking for the area bound by the function and the x-axis. So we're looking for this area in here. And to do this, we're going to use the integration that we've learned. So we're looking for the integral with a lower bound of 8 and upper bound of 14 of the function the square root of 32 minus 2x. I'm going to write that using exponent form. The reason being it's going to make it easier for me to find the antiderivative to do the integration. This is going to be equal to, kind of do this in steps. I know that the outside function was a power function, 32 minus 2x. I'm going to raise that to the 3/2 so that when I take the derivative of all of this and I take the 3/2 and increment it down by 1, I'll end up getting the 1/2. But then that would mean that I would end up here when I take the derivative with a 3/2 here. So to make sure that that 3/2, if you will, cancels, I'm going to multiply by 2/3. And then the other thing I have to pay attention to is that when I take the derivative of all of this, again, I'm trying to take the derivative of this so that I get back to that. So when I take the derivative of this function that I'm building, I'm going to end up using the chain rule. So I got to pay attention to the fact that I have this 32. I have this inside function, 32 minus 2x. The derivative of this is going to be -2. So to anticipate that, I'm going to additionally multiply by -1/2. And then all of this gets integrated from a low end of 18 to a high end of 14. And then when we evaluate that, we are going to get, this will be equal to the high end. The end of this is when x is equal to 14. So that's going to be -1/3 times 32 minus 2 times 14, which is 28, all raised to the 3/2 power, minus the low end, which is going to be -1/3 times 32 minus 2 times the low end, which is 8. So 2 times 8 is 16, and this is all raised to the 3/2 power. And then when I evaluate that, I get -1/3 times 8 minus -1/3 times 64, which is then equal to 56/3. All right. So this integral in example 1, the integral gives us the area underneath the curve. And that's because the area underneath the curve, which is going to be positive, is above the x-axis. As we'll see in the next problem here, example 2, that is not always the case. If we're looking for the area between the curve 3x squared minus 12 and the x-axis. Well, some of that area, this part here, some of that area is going to be negative, whereas the area that's above the x-axis, this area, what I'm highlighting in green, that's going to be positive. So if I do the entire integral, which is what we have here, for example, actually it should say here, example 2.5. So if we evaluate the integral from 0 to 3, well, the area down below the x-axis is going to end up canceling out with the area above the x-axis. So in order to do this, in order to find the shaded area, we have to pay attention to what of that area is below and what of that area is above. So really, to do this problem, we're going to end up doing two integrals. The first integral we're going to do is the integral from 0 to 2. So why am I picking 2? Well, I'm picking 2 because that's over here. That's where we cross the x-axis. So the integral from 0 to 2 is going to give us the area of between the curve and the x-axis, that area that is underneath the x-axis. Right. So we're doing the integral from 0 to 2 of 3x squared minus 12 dx, which when we take the antiderivative of that, you get x cubed minus 12x, and we're looking at that integral from 0 to 2, which, when we evaluate this, we get 2 to the third minus 12 times 2 as the value of the top end of that integral minus the value at the bottom end, which would be 0 to the third minus 12 times 0, or 0. So then this is going to be equal to 8 minus 24, or negative 16. So that's the area below the x-axis. That's negative 16 there. And then if we do the integral from 2 to 3 of 3x squared minus 12x dx, that's going to again be equal to x to the third minus 12x. Now we're integrating from 2 to 3. The upper end of this interval is going to be 3 cubed minus 2 times 3. The lower end of this interval is going to be, whoops, I don't want that to be a minus. The lower end of this interval is going to be, well, it's actually the upper end of the previous interval, so it's the 8 minus 24, or negative 16. So then this is going to be equal to 27 minus 36 minus a negative 16. So we got 27 minus 36 plus 16, and this ends up being 7 total. So then the answer to the question of what's the area, well, we got 16 units of area below the x-axis, we have 7 units of area above the x-axis, so we have a total of 23 units of area. Example 2.5, what's the value of the integral from 0 to 3? Well, then the integral is going to be looking at negative 16 plus positive 7. So that is going to be -9. Make the negative prominent here because that's the important part. All right, so down here at the bottom of the notes on page 1, and then at the top of the notes on page 2, we're going to show you a couple shortcuts for evaluating integrals, and the first shortcut has to do with when the function is even, and then just a reminder that functions are even when they're symmetrical about the y-axis. So a function is even if it's something like x squared or x to the 4th or cosine x. Oops, that's not how you spell cosine, is it? Cosine x. Those are even functions. All right, so, and before we begin this, just a slight modification to this graph that Mr. Friedland has given us. In order to do our calculations based on this graph, what we need is this function to go through the point 7,0. And if the function is going through the point 7,0, it actually is going to end up down here at the point 9, -6. So we're going to change this graph just slightly. Make sure it goes through the point 9. So the significant points over on the right side are at -3, 6, and then here at -5, 6. And we know that we're going to be going through the point -7, 0, and if we're going to be symmetrical, we're going to also end up going through the point 9, -6, or excuse me, -9 of this function. Well, we don't have to find the entirety of that integral. We only have to find half of it, and then we can double it. So if we are able to find the area over here on the right side, then we know that the area over on the left side is a mirror image of that, so it'll be exactly the same size. So the area over here on the right side is the base of 3, height of 6, so that area is 9. We've got an area of 9, 2 groups of those, so the total area is 18. And now if we, actually let's do this. This area here is 9. If we're integrating now from negative, and look at the areas, so we know that in here, this little rectangle here is going to be 12. This triangle over here is going to be 6. And then the triangle that's all the way down at the bottom is going to be -6. So when we're integrating, we have 2 groups of a 9 plus 12. The last piece to the front side here is just sort of formalizing, or rather generalizing, this pattern of using even functions, right? So if we have, so the condition is that we have an even function, then we can say that if we're looking for the integral from -a to +a, right? So we're going from the y-axis to the right a, we're going from the y-axis to the left a, in other words -a, then that integral is simply, or may perhaps easier done, the integral from 0 to +a of the function. Okay, that's the end of the first side of our notes. Part 2, page 2 of 2 will have the second side of the notes.